in my last lecture, and then we'll move on from there. So, yeah, somebody told me that my handwriting is a bit small on the board. So, if you can't see it from the back, you should remind me, okay? So, okay. Right. So, in the last lecture, what we did was, yeah, so first we studied, well, we of course just wrote down the general postulate that we'll use repeatedly whenever we'll do quantum statistical mechanics. So, that was the first thing we did. Then, as a toy example, we did a single free spin half. Well, it's not quite free, spin half degree of freedom in a magnetic field, right? And we calculated the partition function and the average magnetization of this problem, and we saw how that behaved, and so on and so forth. Then we did the problem of one free particle in a box, okay, and two identical particles, again free, in a box. Okay. So, these were the problems that we did, and in particular the last two problems demonstrated something quite nice. A, the role of statistics. It in fact induced some effective correlations between. Oh, so I should write bigger. Okay. Okay. But anyway, I have written this, so I don't want to write this again. Okay, now I'm under pressure, but okay. Yes. You know, whenever somebody takes you out of your habitual things, you fall under pressure, right? Yeah. Okay. Anyway. So, where was I? Yeah. Okay. So, as we saw, even when you had non-interacting but identical particles, due to the fact that the wave function has to be necessarily symmetrized or anti-symmetrized, there were actually induced correlations, which we saw. And in fact, we saw that it was very instructive to write the density matrix, if you wish, in the real space representation. Okay. So, that is where we stopped. And these two things also helped us rationalize in a very natural way why we do this peculiar thing in classical statistical mechanics. You see, I mean, so let's call it x dp for all the n particles you have. So, let's put an index n here. So, you see, in classical StatMech, we introduce this factor and this factor in a rather ad hoc manner, but here when we did this analysis, it came out absolutely naturally, right. So, these are the things to remember from the previous lecture. Of course, you should remember everything, but anyway, these are the main things to write. So, let me just take a pause, and if there are any questions regarding this, I can address them at this point. Yeah.
Why do you say the particles free? Because you are taking the particles in a box.
Yeah.
So,
particle is free up to the boundary conditions of the box. So, the Hamiltonian of the particle is this. This is the Hamiltonian, and what the box helps me is to make somehow the number of modes countable, and then I can regulate that problem and convert sums into integrals nicely. So, and it also provides a volume.
can you impose the condition on the wave function?
Yeah, of course. That's what I did last time. I imposed a periodic boundary condition.
So, you did not apply the condition that the
No, I did not.
function
No, I did not.
bounded.
Yeah, I did not. That's okay. It's my box. I can do whatever I want. No, but to give you a better answer, these are boundary conditions, right? See, typically in many calculations, you choose boundary conditions which make your calculations simpler. Okay. So, if your box is large enough, you could have done what you did and it would have been a harder calculation, but you would have gotten essentially the same answer. So, the reason I chose periodic boundary conditions was it makes the calculation much easier, that is all. If the box is large enough, things will not be too sensitive to the boundaries.
So, I am saying that if I impose a condition that the box is some finite length and the wave function will vary
No, I understand what you mean. I'm just saying that my definition of a box is that there is a periodic boundary condition imposed. I understand. Yes. It's just a question of boundary conditions, nothing more. No, I understand what you're saying. But I'm saying that when the box is large enough, please try that calculation. Since you raised the point, you should try the calculation. It's not a hard calculation. Just do it and you'll see that you'll get essentially the same answer when L tends to infinity. Yes. No. He's asking about the boundary conditions. Anyway, just do it and you'll see that the answer is the same.
Differences are proportional to surface area. And compared to the volume, if you divide on by that, it will go to 0. So it should not matter. So therefore, one can choose also whatever is more
Convenient. Yes.
Sir, and one more definition I remember about free particle is a particle which is not subjected to any external force.
Yeah. So there is no potential here, right? So I did not write any potential term here.
0 for all the
Okay.
That is why Hamiltonian is just tried and
Yeah. Okay. Okay.
There was the case 2πn.
Correct. The quantization condition.
So he had applied the boundary.
Sorry.
He's saying that the purpose will vanish.
No. Yeah. But I just answered that question. I said to him that the reason I applied periodic boundary conditions and not vanishing boundary conditions is because in periodic boundary conditions the calculation is simpler, and if the box is large enough, it does not change the answer.
Loading is always
Of course, it's a valid boundary condition. There is nothing called an in.
continuous, at the end it is continuous, it then affects in the periodic also.
No. I'm not saying it's an invalid boundary condition. I'm not saying that.
Sorry, any boundary condition can.
Okay. Right. Any other question?
one particle in a box, where does the statistical mechanism?
Okay. Yeah. So remember, we were imagining that somehow, even though this is one particle in a box, it's connected to some external reservoir, which is at temperature T, and that's what keeps it at equilibrium. Right. Yeah.
Then this is your deriving something. Okay, you have derived one thing, that's one particle in a box. Then how do you apply it? You have to use the codes or you have to apply
Course.
codes?
Code.
You have to use to actually apply.
But in my last class, I did it in front of you, right?
That is the thing. But actually, actual application to some problem, you have to.
What do you mean actual application? This is the problem here. This is the problem, right? You mean if I have potential or something? What do you mean? I didn't understand. Okay. See, there are some problems which are solvable. There are some problems which you cannot exactly solve, right? So, okay. In this lecture and the previous lecture, we were considering some simple toy problems to illustrate certain general properties. During the course of these lectures, also we'll consider certain toy problems, but they'll capture certain very basic physics which can be gleaned out of that. Let me just give you an example, because it might be confusing to many people, this whole philosophy of considering toy models, Ising model, this model, that model, and so on, right? Because of course, in the real life example, maybe you can say, oh, but I'm ignoring this term, I'm ignoring that term, right? So I hope to show during the set of some other lectures as well, one very basic property which distinguishes a system of, let's say you have an insulator, for example, and you have a metal, okay? Let's say I give you a metallic system and I give you an insulator system. And let's say I measure the specific heat of both of these systems, okay? Right. Then one can show that at very low temperature, for an insulator, the specific heat behaves like this, at very low temperature, okay? Whereas for a metal, it behaves like that, okay? What these numbers A prime, B prime are, of course, depend on the material that you are looking at. But the fact that it behaves like this for an insulator and it behaves like that for a metal are completely robust properties. And then you can try to ask, can I think of a simple model to understand that? And then start from that basic building block and understand other things about the metal or an insulator, right? That's the way to approach a real life problem. Because you see, when you look at a problem and if you want to address it in all its complexity, you'll be completely lost. I mean, so that's not the right way to do physics. I don't know whether that answered your question, but yeah, okay. And for some problems, of course, you need to write codes. For some problems, you can do things perturbatively, so on and so forth. But yeah, anyway, so far so good? Okay, good. Okay, so today we'll start with another simple one particle problem again. But this time there will be an external V of x as well. And then we'll actually try to see how to generalize it to a many body setting so that we actually get this property of an insulator. Okay, that's the goal. Maybe I'll finish it in one class, maybe I'll take two, but that's the goal. Okay, so I hope this is clear, right? This is a very powerful statement. You should appreciate these two statements, right? I mean, there are an incredible variety of insulators that you can imagine, right? All of those insulators, if you look at the specific heat at low temperature, shows you this behavior. This is in some sense a universal fact, right? And there are various material properties which are hiding in this coefficient. So you should appreciate the non-triviality of this statement, both experimentally and theoretically, right? I mean, this should make you surprised. I mean, of course, now that we are all educated, we understand why this happens, but it's surprising nonetheless. Okay, good. No, I said low. I didn't say high, low temperature, low. If it's high temperature, then there's a problem. You see, then your specific heat would diverge if it goes like this, right? And that normally that does not happen for most substances. Specific heat does not diverge. Sorry? Correct. Yeah. In fact, that's called the Dulong-Petit law, right? And that's also an interesting thing, right? Since we are talking about this, of course, as many of you may have encountered, at high temperature, you expect this to approach to a certain well-defined constant, right? And that was the prediction of Dulong and Petit and many other. I'm sure I'm not pronouncing the last name correctly, but anyway, and many others sort of believed that. But then in the early 1900 somethings, there were several experiments that actually showed that this is actually incorrect, both for insulators and for metals. If you read any good solid state book, right, for example, Ashcroft and Mermin, Agents of Quantum Statistical Physics in so far so good. So let's consider this one body problem that we'll think about, and then I'll actually tell you how that one body problem actually can be generalized to give you this physics. So the one body problem that we'll think about is a single quantum harmonic oscillator at a finite temperature. So that's the problem, okay? So all of you have studied the quantum harmonic oscillator problem, right? So here the Hamiltonian is of course not that of a free particle. So here there is some potential as well. So this is not a free particle, right? And we sort of know how the wave functions look like, so on and so forth, right? I mean, look, okay. If I draw them like this and I keep drawing them, I'll make a mistake. But anyway, they look like this, okay, right. Okay, and one more property which is important if we want to solve for the partition function is that we know that we can index all these wave functions by an integer, and for the ground state we can use n equal to 0, for the excited state n equal to 1 and so on. So then this probably you know. What is the energy of the nth eigenstate? One person please. nth eigenstate. Right. This you must have seen how to do. Good. And this is the energy of the nth eigenstate. So then we can calculate the partition function very easily from our general postulate, right? So good, let's just do that. So then it's just this, right? Everybody agrees with me? It's just this. Okay, and this can be straightforwardly done. You can check that whatever I'm writing is correct. So this is the This is the partition function for this harmonic oscillator at an inverse temperature beta. So okay, it's kept like this. Good. Okay, so now given the partition function, how do we calculate the average energy of the system? See, of course, when the system is at finite temperature, there is a certain probability that the system is in the ground state, in the first excited state, in the second excited state, and so on and so forth. So then I need to calculate what's the average energy at a certain temperature, right? If the temperature is finite, clearly the energy is not the ground state energy, it's something higher, right? So I need to calculate that number. So let's just calculate that number. So then I claim that if I know the partition function and I take the log of that and differentiate it with beta, then this is the average energy. Do people know why this relation is true? I mean, have people seen it before? Okay, good. If everybody is comfortable, then I'm happy and I won't explain it. Okay, but it can be straightforwardly also derived. Okay, good. So this tells you how, given the partition function, you can get the average energy. Okay, good. So then this is again straightforward. I know the partition function, therefore I'll just write down the average energy. But if you haven't done these steps, you should try to repeat them, okay? Because these are very simple steps. So then I'll write the answer in a particular manner, like this. Okay. Now, suppose I ask you the following question, that, okay, so clearly this quantum harmonic oscillator, because it is at finite temperature, it has a certain probability to be at the n equal to 0 state, n equal to 1 state, n equal to 2 state, so on and so forth. I ask you, what is the average n? Expectation of n at this temperature, what is this? So could anybody tell me that? Expectation of n, where n is of course defined by this quantum number, right? This is rather just an index. That's true, right? Because we know that the energy by definition is n plus half h cut omega. Therefore, average energy is just average n plus half h cut omega. So this must be average n, right? That's it. Good. Good. So this is one thing which we'll sort of store in a box. It'll help us in deriving this thing. Okay. So this, this is actually a very interesting function. This is the Bose-Einstein distribution function with zero chemical potential. We'll later see what it means, but see, in this example of an oscillator, it's hard to see where there is any boson or anything, right? This is just an oscillator problem. But somehow this thing exactly looks like a Bose-Einstein distribution function, right? I hope people have seen the Bose-Einstein distribution function and the Fermi-Dirac distribution function for free particles. And this should remind you of the Bose-Einstein distribution function, right? Look at the structure of it, right? Okay. So one immediate question is, why is it like this, right? That's one very obvious question. Why is it like this? So we'll come to the answer of that soon. But let me do another thing, which is calculate the specific heat from that. Let me calculate the specific heat from that. Specific heat I can just calculate from this expression by differentiating it with temperature, right? Again, this is straightforward, so I would not, no, I would still recommend you to do it. Yeah. So let me just write down the big expression. It's not terribly big, but there are some terms here, and then we can see some general things here. I hope my handwriting is clear here. Okay. Then in the numerator there is a 1 by t square. So this all is in the numerator, whatever I'm writing now. Okay. This is what it looks like. So all I need to do is to take this and differentiate this, and I get this. Okay. So okay, this looks like some kind of a messy object, right? But at least there are two simple limits here which we can ask. So we can ask what happens when the temperature is very low and what happens when the temperature is very high. Okay. So let's first start when the temperature is very high. Just look at this function and try to tell me what would happen when the temperature is very high. What is the limiting thing that I would get? So just look at this. And the temperature is high, okay? So beta is small, if you wish. No, it won't be 0. So when temperature is high, 1 by T is small, right? So then you can try to simplify the denominator, and this is essentially 1 and all those things, right? So now let me check it. I hope I haven't missed any factors, but let's check. Sorry? 1 by t cube. Oh, okay, that's interesting. Let's see. So let's try to see. Hopefully we haven't missed any factors. That's always the worry. Okay. So I'm at high temperature, right? This is essentially 1 because I'm at high temperature. What else? Sorry? What? No, you can help me if you want. So, yeah, that's correct. This guy, right?
Square.
This guy is square, right?
But then cancels whatever. One cancels, and one is and then one base.
This. Right. Now what do you want to do?
No. I expand this and one I drop. E is not there anymore. E to the power x is just x.
That's correct. This is a small term. This is a small term. So you just keep, yeah. So you just keep the first order. That's correct. That's correct. That's correct. Absolutely. Absolutely.
E and 1 and everything is 1.
That's correct. That's correct. So you pull out a t square on the numerator.
Yes.
Right. Exactly. Right. Right. Right.
And then 1 by t is there.
Ah, okay. So that already means that you should repeat my calculation. Ah, you mean to say this factor should not be there? Okay, let's see. Yeah, because it's highly possible I miss some. Okay. Okay. By kV. Good. Very good. Very good. Very good. Very good. Okay. Good. So I must have made some error of some factor of 1 by t somewhere. So if you correct that, so then one homework exercise is, of course, you just calculate the correct expression. So then Cv goes to Kb as t tends to infinity, because now I have cancelled the powers of t. Right. Good. So this is nice. This is nice because when my temperature is very high, even for these problems, we saw that we recovered the classical limit. Right. So for this problem, the classical specific heat is very simple to calculate. This is quadratic and this is quadratic. So we can just use something called the equipartition theorem. So to the specific heat, I'll get a contribution of half kb from here and a half kb from here. So I should get kb at high temperature. So that's good. So yeah, please just differentiate properly and you'll get this. Good. So at low temperature, what happens? So at low temperature, what would actually happen is this thing will dominate, right? Because then this guy is a large number at low temperature. And there's only one exponential upstairs, but there are two exponentials downstairs, right? So I cancel one and then I can pull up the next one from the denominator. So I'll get like a negative exponential thing and with some factors, right? So, right, exactly. So something like this, some structure like this, right? So see, this is actually a very nice result. So basically it tells you that the specific heat at low temperature is exponentially decreasing. So now this is a general property of any system with a well-defined gap. Okay, even if you take a many-body system and let's say the many-body system has some ground state and then there is some excited state, and then typically what happens is maybe there are many more excited states. And let's say there's a well-defined gap in the spectrum. Then at low temperature, basically if you look at the specific heat would go as something like this. Okay. So in fact, experimentally, if you see this behavior, that typically means that your many-body problem has a gap to creating any sort of excitations in the system. So that's one general lesson we already learned from here, right? See, in this problem there is a gap, right? From the ground state to the first excited state, right? So that's another simple thing to remember. This is also a general property. Okay, good. So now let me come to this question of why this Bose-Einstein distribution comes here, right? Even though we are doing a harmonic oscillator problem. So have people seen how to solve the harmonic oscillator using ladder operators? How many of you have not seen it? Oh wow, that's very impressive. Okay, how many of you completely understand it? Yeah. See, Shamik is asking the right questions. Okay, so yeah, to get the right answers, you should ask the right questions. Right. Okay, but yeah, how many of you remember it and think you understand it? No. That's also a bad statement. Yeah, but I mean, I cannot go beyond think, right? I mean, see, I think I understand something. It may not mean that I understand it, right? I mean, there's a logical thing there, right? So. Okay, let me put my question like this. Do you think I should repeat the ladder operator thing here or not? Just give me an honest answer. Otherwise, I can go on. Okay, I hear 3 no's, but the others are just sitting like this. So you have to tell me something. Yes or no, something. I'm just asking. Good. Yeah, I'm just asking that, see, this is the oscillator problem, right? And you get a Bose-Einstein function here. So I'm just asking that, do people know how it comes about? And if people really understand the ladder operator formalism of doing a simple harmonic oscillator, then the answer is yes. So I'm asking whether this is clear. I mean, No. Yeah. Okay, let me do it. Yes, okay. There are enough. Yeah. Okay, let me do it. Yeah. I mean, of course, yeah, you are right in one way. I mean, I got the answer. Then you are asking me, why am I belaboring the point that this is something connected to some Bose-Einstein function, right? I'm just trying to tell you where do the bosons emerge in this picture. That's all. So let me anyway do it. Anyway, I won't take more than 5 or 10 minutes or 15 maybe. That depends on your speed as well. But let me anyway do it, I think. Yeah. Okay, good. At least I have 2 voices of support. That's enough. Yeah. In academics, we should not live in a democracy. Oh. Recorded, right? Anyway. Right. That's okay. I qualified my statement. Okay, good. So let's do some of the initial steps fast and then we'll approach the main problem. So again, I just write this Hamiltonian. And now we'll think of an alternate way to solve this problem. Okay, that's the point. We'll think of some other way to solve this problem. So how do we want to solve this? We actually define. So see, these are all Hermitian operators, right? X is a Hermitian operator, P is a Hermitian operator. Now I'll define 2 non-Hermitian operators, and the motivation for that will be soon clear to you. Okay, so let me first define my first non-Hermitian operator, and I'll try to get my factors right. But you see, you should always check all the calculations because it's very easy to make some mistakes of factors. So, okay, not in an exam though. Please don't make those mistakes in an exam. Okay, good. So, can people see easily that this is a non-Hermitian operator? Why is it a non-Hermitian operator? Yeah, that's correct. So, let's just write the A dagger as well. So, what is A dagger for this operator? Yeah, and of course this guy. Don't forget your constants in an exam. Yeah, now you can forget them. Oh, but then it'll be a problem. If I forget them and they forget them, then, yeah, right. Okay. Yeah. Right, good. So now, let's write the Hamiltonian in terms of A and A dagger. That's very simple to do. So the Hamiltonian is, this is the Hamiltonian, okay? So this object is Hermitian, right? You can easily see A dagger A is obviously Hermitian, and it has to be because Hamiltonian is a Hermitian operator, right? Good. Okay, so far so good. Now by some convention, I'll call this operator as some kind of a number operator. We'll soon see why. Okay, good. So far so good. Now let us try to do something. Let's try to calculate this commutator. Can someone tell me what is this commutator? You should not tell this. Come on. When I say, you would hopefully know, or hopefully be able to do it. Hopefully. Don't do it, or do it in your head. Okay. So let's just try to do it, right? I mean, yeah, you can just use the commutation relation of x and p. Actually, let me try to make your life simpler. I get your point. I mean, what is the commutation of, see, you know this guy, right? This is true. Now let us take a step back. Let's first calculate this guy. Thanks, that's a good suggestion because otherwise it's a bit messy. That's true. Let's first calculate this guy. Yeah, let's see what this is, right? So all the information is here, right? And yeah, so those who like literally know the answer, then they can stop declaring the answer. Those who want to just calculate it and don't, yeah, they should just try to. And So you just need to insert this definition of A and this definition of A dagger and just expand the commutator and use this, right? So who said identity? You did it right now? Okay, good. Then I'll take your answer. Okay, but for the others, please just do it carefully and you will see that it's just, yeah. Or you can also write identity. Yeah. Good. Now, once we know this, now please try to do this using this algebra. So you just need to now use not this expression of H, right? But you should just use this expression of H, right? And then you know the algebra of A and A dagger, you can do it. Huh? No, no, just do it. No, 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 it's not A. There is some factor also. Factor is important. What is it? No, 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 it's something else also. There is also some, oh well, I'll just tell you the answer if I tell you that. See, when you're doing commutators, etc., even signs are important, right? I mean, AB commutator is not the same as BA commutator and so on, right? So just be careful about that. Yeah. Anyway, that's absolutely correct. But let me actually just ask people something. I mean, suppose I have an operator of this structure, right? How do you go about, because this is essentially the structure there, right? How do you go about calculating the commutator? Okay, so they know it. Good, good, good. And of course, you have to be careful about where B goes and C goes and so on and so forth. Good. And that's all you need and you get this. Good. So now we gather some speed and I'll just write what you need. So we calculate this commutator, we calculate this, and the other thing that we need is for the dagger, and that comes with a plus sign. Okay? Good. That's okay. That we can, yeah. It's okay, we can live with this for now. Yeah. Okay, so now why did I introduce these A's and A daggers, you may ask, right? Because this seems very weird. Why did I introduce this A's and A daggers? So here comes the crucial property. Suppose phi of E is an eigenstate of this problem, right? Suppose it's any one of these eigenstates of this problem. Okay. Now let us ask, if I hit this state vector with A, so I do this, right? Then is there some simple interpretation of this, right? That's the question. So I already told you this is an eigenfunction of this Hamiltonian. Now I want to see whether this object, which is another state vector, is something nice, right? That's the aim. Good. So then, for showing that in the quickest possible way, I'll use this this relation. Okay. So how do we do that? So I'll just hit this operator on this guy, right? But I know that this guy is exactly this guy. So I know that this is the right hand side I'm going to get, right? So far so good. This is the right hand side that I'm going to get. Good. So now let's actually expand this, right? So if you actually expand this, so you can try doing this. So you just try to expand this and then does it tell you something immediately once you take things properly on the right hand side and the left hand side? So just expand this and use the fact that this is a energy eigenstate of H. With let's say an eigenvalue E. Okay, so let's just use that notation. So just expand this and yeah. This should not take so much time, but okay. So yeah, so if I just apply H on this guy, I'll get this guy. Just by this equation, I won't need to use anything else, right? So then what did we learn? That if I have an energy eigenfunction and I apply this A operator on that, it gives me the energy eigenfunction with which is below that, right? So that's why this A, this operator A, is called the lowering operator. Similarly, I just leave it to you to verify. You now just have to use this relation, this second relation. I leave it to you to verify that if you do this, then you just go to the next eigenvector, energy eigenvector, and therefore completely on reasonable grounds, this is called the raising operator. Okay, good. So far so good. Now, so then you see, if I then tell you the ground state or any other state, it's actually very straightforward to create all the energy eigenstates just by applying this operator repeatedly. Okay, just by applying this operator repeatedly. So you need to work out some normalizations, which I leave as an exercise. So if you want to create the nth eigenstate, then all you need to do is, of course, naturally hit the ground state by a dagger n times, right? Because if you hit it the first time, you get n equal to 1. If you hit it the second time, you get n equal to 2, so on and so forth. So the only non-trivial bit is you need to work out the normalization here, okay? And this you can again work out just by the information given here, okay? So acting on n equal to 0, which is the ground state, okay? So this is how the nth eigenstate looks in this language of these non-Hermitian operators, okay? Right, good. Another thing which is very important is if you act this operator, on any energy eigenstate, you'll actually get back the index n, okay? Right, good. So, okay, so now these are actually all the properties that are shared by creation and annihilation operators for bosons, okay? So, I don't know how many of you have studied second quantization. So, in the second quantization language, if you just think of bosons, so I won't really want to introduce second quantization here because soon it can get very tedious, okay? There are much more basic things which I want to explain first. But anyway, so in the second quantization language, what you actually say is that there are some creation and annihilation operators, and if you, roughly speaking, if you hit some state with the creation operator, then basically you create quote unquote one more quantum of that, right? So why that word? Because this guy is like the number operator, right? So it can only be integers, right? And if you hit it by A, then you actually destroy one quantum, right? Good. And for a many body system, typically what happens is for a bosonic system, see here this is literally like just one species of boson and its number can change. That's the only thing which can happen here, right? But for a many body system, what happens is you have to supplement this. So then this becomes a Kronecker delta like that, and then you need two other relations. That's correct. That's correct. So basically you may wonder what these numbers alpha and beta are. So for a many body system, you can ask, let's say I take a general boson system, and let's say the system has some conserved quantities. For example, momentum, right? Then typically you can use a basis where this alpha and this beta are both momenta, but different momenta. You remember this box problem, right? So in the box problem, when there were several momentum levels. So this momentum can have many values. And for each momentum, you have some effective boson problem living there, right? So that's the description. That's the many body description, if you wish, right? And we'll soon see an example where that literally happens, okay? When we consider the specific heat of insulators, right? Good. So this is the simplest example where there is only one such index, right? So anyway, I don't need to care about this relation, I don't need to care about this relation, right? Because since there is only one index, A comma A is of course always 0, that's the same operator. A dagger comma A dagger commutator is again always 0, because that's the same operator. So the only non-trivial relation is this, and I'll get identity here, right? And that's exactly what I get, right? So this simple harmonic oscillator is really the, if you wish, one boson problem for you, where the only degree of freedom that you have is the number of quanta of that bosonic problem that you can create, right? That's essentially the idea, okay? So that's why this relationship comes here. That's why this relationship comes here, okay? Because this is a property of bosons, okay? Good. Oh, there's actually an insect inside, but don't worry. Right. Okay, good. And if you had fermions, then all that you need to do is to replace this commutator by anti-commutator. Okay? In all these three, and then you'll get the algebra of fermions. Okay? Right. I mean, the advantage of this second quantization language is that you really don't need to worry about very messy expressions if the number of particles in your system becomes large. You don't need to write a determinant and keep on expanding things in determinants and so on. That gets very messy very quickly, right? So, okay. So, this part I don't want to belabor too much because I'll really not have the time to explain this. The only essential thing that you should get out of this is actually the simplest realization. This simple harmonic oscillator written in this language is the simplest realization of this bosonic algebra. This is the thing you should remember. Okay? This is really the simplest problem where this occurs, and that's why this occurs. Because you see, this n is really effectively the boson number. And that's why, since it's a boson number, it follows the Bose-Einstein distribution. Okay? Good. Correct, correct. Because you can show that this n is an integer. I mean, here you can just show from whatever I've written that this n is precisely an integer. N can be 0, 1, 2, 3 till infinity. So it's really effectively counting the quanta of bosons, if you wish. Yeah. No, I mean, you have to express the problem like this. Yeah, okay. So you can think like that. Yeah, the nth state is effectively like n quanta, right? So the way you're thinking about creating all these states is, there is a ground state which you effectively call vacuum. So let me call that a ground state. So the ground state has the property that if you hit A on it, you'll get a 0. Why is that? Because the ground state must have that property. I mean, look at this expression. Look at this expression. If you hit A on a state, on an energy eigenstate, it lowers the energy by h cut omega. So suppose I tell you that a state is a ground state. Then there is a contradiction, right? Because then the energy would be even lower than the ground state. So the only way to resolve the contradiction is you must get a 0 on the right hand side. So in fact, using this relation, so you know how to write A in terms of x and p. Using this relation, this is the differential equation. If you just express it in the position basis, for example, using this relation, you can find the ground state, in fact. And when you find the ground state, after that, applying A dagger on it, you can find all the other eigenstates. So yeah, you're correct. The interpretation is, okay. The interpretation is that you are repeatedly producing multiple quanta of this boson, and that's effectively like representing these states.
I'm sorry, I didn't get that. Alpha and beta are the
There are many now. Wow, there is a swarm of them. Anyway, yes.
Alpha and beta are nice going over which quantity?
Sorry. So this was I was discussing the. Be careful. Yes. This I was discussing the many body problem. The many body problem. So see, what is the philosophy? So in a many body problem, you don't have just one bosonic degree of freedom. You have many bosonic degrees of freedom, each characterized by its own quantum number. You may ask what that quantum number is. Typically, the best way to think about this is you take your system and ask, is there a good conservation law there? For, let's say, a system which has translation symmetry, momentum is a natural choice. Then basically, a good basis to think about this is each of these different alpha is a different momentum, right? And you can think of the problem in that basis. So you can represent any many body state by a bunch of these bosons or quote unquote effective harmonic oscillators, each living at a different momentum. That's it. That's a complete basis. So for a boson system, this is really the definition. So see, remember the bosonic systems satisfy symmetrization properties? I said in the first class. So the wave function is, yeah? Correct. So, yeah. No. So here it came because I wanted to re-express the quantum harmonic oscillator in terms of this guy, right? Okay. Now, in a bosonic system, in a general bosonic system, I mean, suppose I write something like this. Let's say I have some vacuum state, and then I write something like this, let's say, at some momentum p. That basically means that I have created a state exactly with that momentum p, with some normalization, 1 by square root v, let's say, right? Okay. Now suppose I hit this twice. There is a P1 and there is a P2. So if these guys satisfy this algebra, you can show that this guy, when you write it in the position basis, is exactly the symmetrized version that we discussed about, plus its symmetric partner. So you just interchange R1 and R2, right? So yeah. So see, the nice thing about this is all that you need to worry about is you just satisfy this algebra, and each of these guys is okay, so how did I create this? I just considered the one body quantum mechanics, right? I mean, a dagger acting on 0 gives me some one particle state, right? I of course know the one particle state. Whatever problem I'm solving, there is some natural one particle representation where I want to write it in. Then if you enforce this algebra, automatically you'll get the symmetrization and anti-symmetrization. That's the nice thing. You'll get symmetrization automatically if you do this, and you'll get anti-symmetrization automatically if you do that. That's the key thing. You don't need to, write big determinants or big permanents for bosons. So for bosons, there's something called a permanent of a matrix, which you need to write. Whereas for fermions, you need determinants. And you don't need to write all of that. That's the, so good. So, okay. So now, once we have understood what's the relation between a quantum harmonic oscillator and an effective boson problem, let's actually deal with a problem where we'll find that there are many quantum harmonic oscillators at all different frequencies, and we'll try to understand what's the finite temperature response of that. Now you will ask me, what is such a problem, right? So there's a very natural problem for that. Consider an insulator. So in an insulator, suppose I go to very low temperature and then I try to study the specific heat. Now at insulators, you know that it takes a lot of energy to move electrons around, right? That's why they are insulators, right? So at very low temperatures, you can effectively forget about the electronic degrees of freedom because they are insulators, right? However, you cannot forget some other degree of freedom, which is the vibrational degrees of freedom of a solid, or what you know as phonons, right? Okay. So then, how do we get this thing? How do we get this thing from such an analysis? That's the question. Okay, right. So now I'll quickly do some analysis which you must have seen, but I'll just point out one or two crucial things about that analysis, and we'll see how this law comes about. So is everybody here aware of the concept of normal modes for oscillating systems? Okay. So okay, so basically the idea is that suppose you have some very regular crystal, right? So let me just draw it in one dimension because it's far easier for me to draw it in one dimension. And these springs just denote some restoring forces in that crystal, right? So basically the crystal is formed and the atoms are staying at some reasonably well defined equilibrium positions. And of course, if you move the atoms around by a tiny bit, of course, if you move them by a lot, then you can break or melt or shear the crystal, right? But if you move them by a tiny amount, the crystal is not destroyed. That's the property of a crystal, right? And then what happens is the atoms basically do some motion around their equilibrium positions, right? So of course, the interaction between these atoms, so let's first effectively think of a classical problem. The interaction between these atoms, whatever they are, they might be some very complicated objects. But if you just do some small displacements around the equilibrium position, then the Hamiltonian is just a quadratic Hamiltonian of that displacement. That's because this is at equilibrium. So you just do a Taylor expansion of your energy around equilibrium. The linear term is absent in the Taylor expansion because this is at equilibrium. And then the first non-trivial term that you get is quadratic, right? Now, of course, if your displacements become larger than that, then of course you have to take the third order term, fourth order term, so on and so forth. But if you just give the restriction that the displacements around the equilibrium are small, then it's a quadratic problem in X. And of course, it's a quadratic problem in P because the kinetic energy is just P squared by 2m for each particle, right? So it's a quadratic problem both in P and in X, right? So because it's quadratic, it's solvable. Okay, so this I assume you have already done in classical statistical mechanics and even before that in your classical mechanics courses, right? So because a Hamiltonian which is quadratic in X, if you think about its force equation, you can just write down the Newton's laws for it. It's basically just a bunch of harmonic oscillators, right? And then all that you need to do is do some variable transformations to make that evident, and those variable transformations are called normal modes. Okay, so that's all there is to it. Okay, so the most familiar problem that you might have seen is, so just to illustrate, I mean, let's say there is a bunch of particles of mass m, each connected to some identical spring with some given spring constant, right? Then for this problem, one can just find the all the frequencies for all the normal modes that you can have, right? So yeah. So I mean, have people done this thing? Otherwise, I can explain very briefly how to do this. I mean, suppose I give you this problem in classical mechanics, right? So there are these identical masses and they're connected with identical springs and you do small oscillations. Then the question is, can you calculate all the normal modes of this problem? Is there anybody who has never seen or heard of such an exercise? Okay, so that means that everybody has seen this. Good. Okay, so then you can calculate the normal modes of this problem. So if you calculate the normal modes of this problem, you'll see something like this. So basically, this problem has, oh sorry, this is very bad notation. So let me use some other symbol G here. So see, this problem has translational invariance, right? So typically whenever the problem has translational invariance, it's always good to go to Fourier space and do that problem. And because anyway you want to, see, anyway the normal modes of this problems are like wave solutions, right? So it's always, I mean, you can always try a solution like this. Right? That's the basic idea. And you can put it in the equations of motion and you can try to find the relation between omega and k. And that's what I'm trying to plot here, right? Good. Good. So now let me ask you a question. So for this problem, this kind of a problem, do you think that the range of k that I would take, do you think that is finite or infinite? Sorry? Okay, so the k range goes from plus infinity to minus infinity. That's what you're saying. Is there anybody who has a different opinion? Sorry? No, no, so I have specified the problem, this one, right? So let's say I'm in one dimension. What repeats itself? Which pattern? No. This is of course the pattern of the crystal. It's a periodic pattern. But now you have to think of the displacement, right? So of course you're right, but you have to think of the displacement field, right? So let's say you displace this guy by a certain amount, UNA. Let's say this is the nth point, right? Then let's say I displace this guy by some slightly larger amount, UN plus 1A. So this I displace by some other amount, right? So there's this displacement field, right? And then when you think of normal modes, basically you're looking for solutions of some form like this. Of some form like this, right? Clear? Sorry, sorry, what? What has a period? What do you mean by period of 2 pi by a? What is a period of 2 pi by a? You are maybe on the right track, but yeah, can you just expand on it? Oh. Let's say we apply the periodic boundary condition. That just gives us the discretization of k, right? That just tells us that the separation between different k is something like 2 pi by capital L. That's all. But I'm asking something different here, right? So suppose L is very big, then that just means that the distance between two consecutive k modes is very small. That's all it says. So it's not related to just the periodicity, right? It's related to something else. No, but you don't need to even look at the equation of motion to answer this. No, okay. No, okay. I give you this solution, right? See, there's a crucial property of this solution. You are not interested in all values of x. I did not write xt minus omega t, right? Because see, all I'm interested in is the displacement field here, here, at some regularly spaced points, right? So I'm just interested in that displacement field. So that's why this is some n times a, where n is an integer, right? So now let me change k to k plus 2 pi by a. Let me just do that. And you substitute it here. Can you see what happens? It'll be exactly the same, right? What is the reason for that? The reason for that is you're not doing a Fourier transform of a function which is defined at all x. This Fourier transformation is just defined for a function which is defined on a discrete grid like this, here, and so on, right? Okay, and that is what gives you this notion of a Brillouin zone. Okay. Yeah. Because whatever k values I take, I mean, it's appropriate to just take an interval of 2 pi by a, because if I take any other bigger interval, there are some k's which map to the original interval, right? So you don't want to overcount. Now the reason for that, if you want to think of it intuitively, is that So you said periodic boundary condition. So that's a property of large L, right? That's like a large L property. So that in real space, it's like a large L property. So in momentum space, in K space, it gives you this small k structure, right? And then there is a, sorry?
First value after 0. I mean, the L will give you the first k value possible after 0.
Yeah, but it will also give you the spacing between the different k. That's what I mean. Okay. Yeah, exactly. If L is very big. And we also use this property to convert sums to integrals, right, regularly. And the second thing is, at the small length scale, there is again this sort of notion of a cutoff length here, A, right? And that, this small length scale gives you in momentum space this cutoff, this bigger one, right? Clear? So if you wish, this is the way to think about it, right? So if there were no cutoff here, so if x was allowed to take any possible value, then there would be no notion of a Brillouin zone, right? So this is the physical way of remembering.
Why does the larger cutoff come from?
Which cutoff?
The larger cutoff.
Oh, because you see, you're not looking at this function at all x. You're just looking at it at discrete x. And this, the discreteness in real space is A. And then when you look at it in Fourier space, that gives you this 2 pi by. Right. You see, because there's this inverse relation between distance and momentum, right? So this is a simple way to intuitively remember it. Then you never get confused.
Okay, but what was confusing me was the fact that even if you have discrete like masses,
Regularly spaced.
each mass's position is something that you can measure.
Absolutely. But that position function, if you wish, is just defined on a set of integers, right? That's all. You just need to specify this u at NA. That's it. U at 0, u at A, u at 2A, u at 3, and so on. That's it. You see? And that is why this thing comes out, right? Yeah. Okay, good. So far, so good? Yeah.
For example, A equal to 0, this bound will
Correct. Absolutely. So one way of thinking about x being a continuous variable is you just take A to be 0, A tending to 0, and then of course this thing will just go from minus infinity to plus infinity. Right. Good. Okay. So now for this problem, since all of you said you're familiar with this, can somebody tell me what is the dispersion of these modes going to look like? Okay, so what is it at small k? Linear, right, that's very important. So it's basically linear and then it tapers off here, right? So, and it has to be a symmetric function. So my drawing is not so good, but it is a symmetric function. Okay, good. So this is how the dispersion looks like. The important point is here it's linear. This is linear. That's very important. Okay. Oh, do you want me to just jot down the steps, like, or I can tell you privately, or, but does anybody else have this question here? Then I can take 5 minutes to tell you, or 3 minutes maybe. You don't seem, you want me to tell this? Okay, good. Since I see some faces so I think the simplest way to do it, there are many ways to do it. The simplest way to do it is just write the equation of motion of this problem, right? So, good. So these are just a bunch of springs. So I'll write the equation of motion. And of course, please check my equations of motion, but probably it's correct. So I'm just writing Newton's law and there's a restoring force on each particle, right? So let's say I look at the, this guy. Let's mark some guy here. So let's say I look at this guy, and sorry, let's just remove these things now. This guy. Then of course, you'll feel a restoring force due to this thing and due to that thing. right? Good. And of course, how much this spring stretches or compresses is determined by, for this spring, this displacement field and this displacement field, and for this spring, this displacement field and this displacement field, right? So let's just use that. So okay, so this is your differential equation. Then the second step is you should just assume periodic boundary conditions, because that always makes life simpler. You can use Fourier transformations, so just use that, right? Good. Then you actually try this solution. You want a traveling wave solution, so you just plug it in. If you plug it in, you'll automatically see that there will be a relation between omega and k. That's it. This equation will automatically determine it. Good. So please try this at home. This is very simple, right? And I mean, even for things you know well, it's always good to sometimes repeat them, right? So that's it. Okay, good. Sorry, again bad notation. Originally in my notes I wrote K, but then here I wrote G, so this is G. But that's it. The rest is correct. Okay, good. So far so good. Okay. So that was one thing. The one thing to appreciate here is that, see, unlike your original harmonic oscillator problem that we did, which I erased, here, you see, when k is very small, so see, this is again a bunch of harmonic oscillators, right? Because what you can show, when you break up the thing in normal modes, each harmonic oscillator at omega is just living its own life, right? That's why we go to normal modes, because then the different oscillators are not talking to each other, right? And this omega is basically the frequency of that, and if you just go to the quantum version of it, then of course it's like a problem with n plus half by 2 h cut omega at that k, right? That's the quantum version of it for each k, right? So now you see how is the analog of what I wrote down there coming. Right? You see, so the alpha here is replaced by the k there, right? So there are many kinds of bosons living, right? So that alpha is replaced by the k there, right? So that's a very simple illustration of that, right? Good. The second thing is, there are oscillators here which have frequencies very close to 0, right? So you see, remember I told you that the specific heat of any system which only has gapped excitations is exponentially small in temperature, right? But see, this kind of a system may violate this, because there are excitations here which basically cost me as small an energy as I want, right? So these are called gapless excitations, right? So suppose you want to like create an excitation at a certain frequency omega, right? So then of course the energy cost to create that excitation is something like this. But see, this number, depending on what your k is, can be as small as you want, right? Of course, if you're here, then of course there's a finite energy cost, but there are many possibilities to create very small energy excitations, right? That is why the specific heat may not be exponential. Now the second order task is to calculate what is the specific heat, right? I don't know whether I'll be able to do that today, but let me go on and illustrate one more point. So of course I told you how to approach this problem, right? Now I'll just slightly deform this problem, because I want to illustrate something very important. Suppose, you see, in this problem, each of the springs had a spring constant of g. Now suppose I make some other problem where, maybe I should use two different colors now. There are two types of springs, okay? Alternating two types of springs. And of course, again, it's infinite or a very large system and so on. So let's say this is some G1 and this is some G2, right? Good. Now you can again use exactly the same equation of motion approach and get its dispersion or the normal mode frequency curve, right? You can again use exactly that approach. Now, now I'll tell you what the dispersion here looks like. Okay, so basically you'll get something like this, but you will also get, so let me draw it with yellow for no particular reason. So you'll also get something like this, another branch here. And see, yeah, I know it's very late in the evening. Yeah, yeah. Anyway, so you see, this branch is always gapped. This branch is always gapped, and this branch can be gapless, right? Okay, and maybe you are familiar with some names like acoustic and optical. Does anybody know why they are called acoustic and optical? Why are they called acoustic and optical? No, that is a correct answer, but there's an even simpler answer. Let's say I don't even look at frequency ranges and stuff like that. There's an even simpler. What? No. I mean, see, for these kinds of things, you can have these U fields can be like this, like that. So yeah, that's not, yeah. So one reason is, see, here you can understand just by looking at the structure of this problem that here, if I have to think of the unit cell, then it's a unit cell like this, right? It's a two-body unit cell. And I mean, that's why you have in fact two branches here. If you just think carefully of Fourier transformation, that's why you have two branches here, because the unit cell has two points in it. So it's a Brillouin lattice with a two-point basis. That's what, if you wish, is the textbook language. Okay, good. So now you can ask yourself whether object 1 and object 2 here, whether they are oscillating in phase or out of phase for a normal mode. So for these solutions, they oscillate in phase, and for these solutions, they oscillate out of phase. Now, typically, let's say I want to make an oscillation using some electromagnetic field. Typically, these kinds of situations are like when something is one kind of an ion and something else is another kind of an ion, like NaCl, for example, right? And therefore, they are oppositely charged. So therefore, of course, if I put a reasonable electromagnetic field, you would expect that one thing oscillates like this and the other thing oscillates exactly the reverse of that, right? So that's it, right? So this mode had to be excited using electromagnetic fields, if you think like that, right? These are much more susceptible to being excited with electromagnetic fields, right? That's why it's called optical and acoustic. Of course, this reason is also correct what you said, but I think this is a more basic reason, right? So, okay, good. So now, please see one striking thing here. The number of, the structure of your dispersion became more complicated. It became more complicated, but this linear part survived. In fact, you can go to the internet, you can go to Google and ask to see more complicated calculations of normal modes for even more complicated crystals. You will see in all of them, just by looking at them, you will be able to identify many acoustic branches and many optical branches. Maybe something more complicated will, oh, I should have used 3 colors, but you all understand what I'm doing. Maybe something will look like this, and then maybe there'll be something like that. Oh, sorry. Maybe there's something else like that. So there are many possible branches, but the key point is that there will be these branches which will go linearly in K. It will be gapless and they'll be going linearly in K, and there will be other branches which are gapped. Okay? Sorry?
Omega key is K square.
Where? No, but these are gapped, right? So the leading behavior is that there is a big gap, but yeah, these can be contracted. That's correct, right? But the leading behavior is this gapped, right? K equal to 0, near K equal to 0. Right. That's correct. Good. So, yeah, this is a general property. Now you may ask me whether this fact that there are gapless modes is a completely general property. of any crystal. Of course, I showed you a very simplified model, but the answer is yes. So I would just state something without explaining it because that will take me too far. So see, this is a general thing. If you have a crystal breaks a continuous symmetry, a certain continuous symmetry, and that continuous symmetry is that of translation. Okay. Now, whenever in a many body system you break a continuous symmetry, you always produce gapless modes, and maybe you are familiar with this name already. These modes are called Goldstone modes. So this is one simple example of Goldstone modes. So whatever the complicated crystal may be, if there is a regular structure, if there is some regular structure, for amorphous things more complicated things can happen, but if there is some regular structure, there must be these linearly dispersing modes here, right? So this is completely general. Okay, but of course I utilize this simple calculation to demonstrate this here, right? Okay. So now there are only 2 or 3 minutes left, so I won't embark on the next thing. So in the next class, what we'll do is we'll just complete this calculation of calculating the specific heat from this model, right? And it's very easy now, right? We know what's happening for each oscillator, right? From this calculation. Now there are just some bunch of independent oscillators here. We'll just add all of them and do some integration and that's it, right? So that was the motivation to do this problem. So it'll be very straightforward. And then we'll see that we'll get a T cube automatically. That's it, right? So I think this is a good point to stop, but the key thing, as I said, is for any crystal that you will have these guys, which will actually dominate at low temperature and contribute to the specific heat. Why? Because of course, if your temperature is very small, you can only make small thermal fluctuations, right? And it's much easier to make thermal fluctuations if their energy cost is small, right? And these will dominate the physics. Oh, we will use the statistical approach when we do the calculation at finite temperature. We'll use all the answers from the bosons that we got here. From the simple harmonic oscillator, and that's a boson. So we'll actually use statistical properties here when we calculate specific heat. You're correct. In this calculation, I have not yet used any statistical property apart from doing the diagonalization in terms of normal modes. So it's just a calculation of the energy spectrum. Now I have to fill the energy spectrum. For that, I'll use this, and then together with this, you will see that you'll get a T cube heat capacity at low temperature. So anyway, I can stop now. You can ask me questions because yeah, anyway it's late. So yeah. Correct. So that's correct. So when you start from Newton's equation of motion and you go to normal modes, in the normal mode coordinates, so let's write them by some capital X and some capital P, you will get terms like P square plus X square again, and if you quantize them, you will get exactly this problem again. Exactly the harmonic oscillator problem again. Of course, I did not want to do all the steps because that's just tedious algebra. I don't want to do it in the lecture. You should do it in the privacy of your room. But you see, the physical picture should be clear. I mean, it's, yeah. Any other questions? Okay. If not, then we'll continue discussing this tomorrow. And I also realized that we have heard a lot about phase transitions during many of the lectures. So in one of the tutorials, I don't know which one, I'll actually try to show you mean field theory way of getting a phase transition for the Ising model, which PK also introduced today. And I'll, if time permits, show you how to also show that in 2 dimensions for the Ising model, there's a phase transition. He considered the 1-dimensional case, but I'll try to show that in 2 dimensions also that there's actually a phase transition at a finite temperature. But that'll be in one of the tutorials. So yeah, hopefully the one before lunch, because that'll take some concentration. Okay. I don't know if I have such a thing, but anyway, yeah.